Okay, this is a brand new unit, Unit 5, and we're definitely changing gears again. In fact, you could definitely say that we're not even learning about functions anymore. Like we've pretty much finished learning about all the other kinds of functions there is to urgently know about, as you potentially move on into calculus and beyond. So like we've already learned about the trig functions, and then we just got done learning about the exponential function and what exponential functions are, and then what logarithmic functions are. So definitely changing gears into something different, and it's sequences, induction, and probability. Whoa. And actually this part of the thing, not to get too far ahead of myself, but this induction part of it is going to be like an entire bonus section. The whole section will result in like a bonus opportunity question on the eventual test. Anyway, here we go. Section 5.1 is about sequences and summation notation. Alright? So, what the heck is a sequence? Well, let's kind of ease our way in. An example of a sequence, one of the more famous name brand sequences, is the Fibonacci sequence, which starts off like this, and it goes 1, 1, then 2, then 3, 5, then 8, 13, 21, 34, 55, 89, and this sequence can go on forever, okay? And a sequence is just like a list of numbers, and there's usually some kind of mathematical stuff going on with how the numbers progress to the next number and to the next number. So what do you think? Do you think there's some kind of mathematical pattern to this Fibonacci sequence? Well, turns out that in order to get the next term, and these numbers are all called terms, in order to get the following term, you add the previous two terms. So it starts off with just 1 and then 1, but especially after that, it's clear to see that 1 plus 1 is 2, and then 1 plus 2 is 3, and 2 plus 3 gets you 5, and 3 plus 5 gets 8, and skipping ahead, it's like 34 plus 55 makes 89, and the next number, and again, this keeps going on forever, the next number is whatever 89 plus 55 is, which should be, 144, I think? Something, whatever. Anyway, moving on to actual notes, the letter A with a subscript is used or can be used to represent values of a sequence. So this whole subscript business is going to be very important for us to become comfortable with. And so that means the first term is represented by A sub 1. A subscript of 1 for the first term. The second term, you guessed it already probably, is represented by A sub 2. The third term, well, shockingly, A sub 3, and so on. Okay? So again, like the subscript represents or denotes which term you're talking about. So the notation A sub n would sort of represent the nth term or general term of a sequence. And just real quick, it's not exclusively the letter A. It's pretty much like the default variable letter that we use. But any lowercase letter can be used, and they tend to be lowercase. The next one people might pick would be like little b, but anyway. And so the entire sequence is represented by a sub n in these curly braces, but not exactly earth-shattering details here. But so a sub n represents the nth term, just because if you had like a sub 9, that would be the 9th term. A sub 12 would be the 12th term, and so a sub n represents the nth term. It's kind of open-ended that way. And so here's like what you might see in a textbook, maybe. Definition of a sequence just kind of goes like this, like I already pointed out with the Fibonacci sequence. A sequence is really just a list of terms, and a sequence can be infinite. It can go forever and ever and ever, but it also can end. So first term, second term, third term, until we basically get to the final term, the nth term, whatever. And if this is the nth term, then this would be the n minus 1 term. And let's get into some examples. So the directions say to write the first 4 terms of the sequence, and we're representing the sequence by this nth term formula or expression or rule, or there's all different kinds of ways all different kinds of words you can use. So we're saying that the nth term is always going to be 3 times n plus 4. Well, what that means is a sub n, whatever n is going to go there. So if you were finding like the, I don't know, I'm just trying to think of a random number, and I don't know why it's taking me so long. If you were looking for the 8th term, a sub 8, that should be equal to 3 times 8 plus 4, and then whatever that is, 28, I believe. But the directions want the first 4 terms, which would be a sub 1, a sub 2, a sub 3, and a sub 4. And so to figure out the first term, a sub 1, it's going to be 3 times 1 plus 4. And then the second term, a sub 2, is going to be 3 times 2 plus 4. And third term is going to be equal to 3 times 3 plus 4. We're always just plugging in for n the term we're trying to find. A sub 4, the 4th term, is going to be 3 times 4 plus 4. And so all these just end up being like pretty easy number crunching. 3 times 1 is 3, plus 4 is 7. 3 times 2 is 6, plus 4 is 10. 3 times 2 is 9, plus 4 is 13. 3 times 1 is 12, plus 4 is 16. And so that's really how it works. The nth term formula, the nth term rule, the nth term expression, equation, whatever. It's just the general term where like it's open-ended, 3 times whatever plus 4. Like, what's 3n plus 4? Depends what n is. Depends on which term we're talking about. And so think about this, people. With an nth term like this, could you skip ahead to like the 100th term? Can we just skip ahead, to finding the 100th term? Yeah, totally. All you'd have to do is plug in 100 for n and get 304, I believe. Anyway, example B, there's nothing really that new about it fundamentally. It just is a little bit uglier. I mean, this still is the nth term. It's got a couple places you have to plug in for n. Like, yes, this does say negative 1 to the nth power, and yes, this does say 3 to the nth power, and then minus 1. So you're still just going to be plugging in 1 for n if you're going for the first term. You're still just going to be plugging in 2 for n if you're going after the second term, and so on and so forth. Plug in 3 to get the third term, plug in 4 to get the fourth term. And then from there you just have to be like extra careful crunching this out. Like negative 1 to the first power is negative 1, and then 3 to the first is 3, minus 1 is 2. Hey, negative 1 to the second power is positive 1. And then 3 squared is 9, minus 1 is 8. So this is going to be positive 1/8. But this is going to be negative 1 down here. 3 to the third is 27, minus 1 is 26. And then it's back to positive 1 up here. And then this ends up being 3 to the fourth should be 81, minus 1 is 80. So hey, I'm just saying, you know, you're welcome for this extra inside scoop. I want you to notice how these terms alternate their sign. You know, it goes from a negative first term and then a positive, the next term's positive, and then we switch to a negative, then we switch to a positive. If we found the fifth term, it would go back to being negative. It's alternating signs, and it shouldn't be that confusing. It's not that big of a mystery what's making these terms alternate from negative to positive, negative to positive, negative, positive. It's this negative 1 to the n portion of your nth term formula. So I'm just saying, if you remember that detail, then you have a really good opportunity to get a bonus point on a future quiz or test or something. Moving on to something called recursion formulas. All right, we're getting a little bit deeper in the water here. A recursion formula. This is where people some people tend to lose their mind here and start to get confused, but that's not going to happen with you, right? So a recursion formula defines the nth term of a sequence as a function of the previous term. What the heck does that mean? Well, you'll see in a second right here. So here's an example. Find the first 4 terms of the sequence in which a sub 1 equals 5. Well, that's the first term. Find the first 4 terms, and they give you the first term for free. And here's what the nth term is equal to. 3 times this, and then plus 2. Well, what the heck is a sub n minus 1? Okay. How should I say this just now here? Well, let's say you're finding the 10th term, which technically means that n is 10. So a sub 10, you're finding the 10th term. And let's say that you're just going to kind of, just like we were, on the last problem, plugging in 10 for n. Well, guys, you need to see that this n minus 1, that whole n minus 1 is your subscript. Okay, it's a sub all that n minus 1. So if you were to plug in 10 for n, this would actually become 10 minus 1, which is 9, and this would become a sub 9. Well, people, what's a sub 9 even mean? What's a sub 9 mean? Well, that means the 9th term. So it's going to be, so basically the 10th term is going to equal 3 times whatever the 9th term is plus 2, right? So that's what this means up here. In order to figure out a term in a recursively defined formula sequence, right? You need to know what the previous term is. And so people, listen, in general, this a sub n minus 1 thing, you need to just kind of think of all the time as the previous term. So whenever you see this, a sub n minus 1, what that is really saying is the previous term. Because n minus 1, it's like you're going back a term. You know what I mean? So here we go. If you're finding a sub 2, when you actually go through the motions of plugging in 2 for n, all that's really going to happen is it's going to become a sub 1, the previous term. And what is a sub 1? Well, the good thing they told us it was 5. And so 3 times 5 plus 2 should be 17. 15 plus 2 is 17. Okay, so you see how that works? See the color scheme here? Blue, blue. And then we move on to the third term. Well, to kind of cut to the chase, when we're going after the third term, then this a sub n minus 1 part is going to be now the second term, which we just got done. We just got done finding it. So again, if you were to, well, guess what? I guess I'm not even going through the motions anymore. How about that, huh? Yeah, I'm really fast-tracking this now, I guess, here too. So it turns out that this formula becomes 3 times a sub 2, the previous term, which again, good thing we just found it, and now we're plugging in 17 in for this a sub n minus 1 part. So here we were plugging in 5, but here we're plugging in 17, 10 up with 53. Well, guess what we're going to plug in next for the a sub n minus 1 part? Well, if we're finding the fourth term, this becomes the third term, which is now going to be 53. So you're always plugging in the answer you just got done finding to the next formula to find the next term, because, again, these recursion formulas are like based on the previous term. So remember how I asked you here? Could we actually skip ahead to the 100th term right away? And here, the answer was yes. You could just plug in 100 and get your answer. But guess what? Could you just skip ahead and find the 100th term with this formula? And the answer's no. Because you can't figure out the 100th term until you know what the 99th term is. And you don't know that until you get the 98th term. And you don't know the 98th term until you have the 97th term. And you don't know that term until you have the 96th term. See how that works? You need to know the previous term, because you're going to have to be able to, you're going to have to plug in the previous term into the formula to get whatever term you want. Okay? Now, this next note is something you might already be aware of. Factorials. So, I don't know, but if you don't know what factorials all about, check this out. N exclamation point is read N factorial. So, when you see an exclamation point, it's actually an official math symbol. It's not like you read this as N, woo, N. No, it's just N factorial. That's how it's written, this exclamation point. And it's equal to what? Do you know what N factorial is equal to? Well, maybe it'd be more helpful if I said, what's 6 factorial equal to? Do you know what, I know it might be tough with an n and not a specific number. Do you know what 6 factorial is equal to? All right. Well, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. So factorial means you just multiply by the number that's 1 less and then 1 less. So you multiply by all the numbers until you get down to like multiplying by 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. Again, you kind of keep going down by 1, multiplying until you reach 1. And so that actions ends up being 120. 4 factorial is just 4 times 3 times 2 times 1, which is 24. 3 factorial is just 3 times 2 times 1, because you always start with that number there. So that's just going to be 6. 2 factorial, 2 times 1 equals 2. And then 1 factorial is just 1, flat out 1. Okay? So what is n factorial equal to? Well, if you start with n, what's 1 less than n? That, n minus 1. And then what's 1 less than that? That. What's 1 less than that? N minus 3. So this is the same as like always going down by 1 as you're multiplying. So n times, so whatever n is, you multiply it by whatever it is minus 1 times whatever n was minus 2 times whatever n was minus 3. And it's like you don't know what n is, so it's like you don't know when you get down to 1, so you just kind of go dot, dot, dot. It's like whenever you end up getting down to like 3 times 2 times 1, it's unknown because, you know, n could be 50, n could be 2, you know, n could be 8, n could be 3. So whatever n is, you just do this times this times this times this until whenever you get down to like 3 times 2 times 1, until you get to 1, and that's when you're supposed to stop. And by the way, 0 factorial, what does that make 0 factorial? Well, oh my gosh, what's going on? I think it's working. No? Okay, this time. No? All right. Oh man, now I'm getting a taste of my own medicine. I'm punking myself. Come on. All right, I don't even know if this is worth it anymore. What's 0 factorial? What is it? Aha! I knew it. I'm just going to do... Whoa. 1. 0 factorial. Was that worth the wait? Yes, it was. It was worth pranking myself there. Okay? So if you missed class... ooh, man. I wonder if I'm going to remember to get someone up to the board to be pranked by that. But yeah, that was worth the wait because well, 0 factorial, it just equals 1. And I know that's kind of weird, and but you know, I'm not going to talk your ear off about it right now. If you want to ask me in class, or we might look at it in class a little bit, but even in class, I don't want to dwell on this because, I mean, even though there is 1 or 2 pretty good, like, real explanations for why it makes sense that 0 factorial is actually equal to just 1. But you know what? Sorry to have like a kind of a cop-out answer, but just think of this as part of the definition. You know, knowing what factorial even means, you know, the definition of factorial, just think of 0 factorial equals 1 as like part of the definition, you know? So it's like 0 factorial equals 1 because we say so. And I know that sounds like a cop-out, but that kind of is the way it is. But again, there is one or two pretty good actual math explanations why that makes sense. But just go with because I say so, because math says so. So example 3 is nothing really new. It's just, let's see, is this recursive? No, this is kind of comparable to these first two examples, except, it involves a factorial. Big deal. We're still going to just plug in 1 for the n's to figure out our first term, a sub 1. To find a sub 2, our second term, we're still just going to plug in 2 for n. And then we're going to plug in 3 for n to get our third term. And we're going to plug in. So that is not anything different. That's stuff I already told you about. So if there was actually one thing that I need to actually emphasize before I just reveal all these answers, it's this. When you have something like this, 1 minus 1 in a bubble factorial, 2 minus 1 in a bubble, 3 minus 1, right? This bubble thing with a factorial on the outside. Listen. Do what's in the bubble first, then do the whole factorial thing, okay? That's what you need to do. Don't I don't even know if I want to say it out loud. Don't distribute the exclamation point, okay? That doesn't make any sense because that would be acting like this says 2 minus 1 times an exclamation point. That's not what this is saying. So don't distribute. Just do the 2 minus 1, right? Just do the 1 minus 1, which is 0. Do the 3 minus 1, which is 2 factorial. Do the 4 minus 1, which is 3. Then do 3 factorial. So this becomes 2 factorial, 1 factorial, 0 factorial, and then the rest of it's just number crunching, nothing new. And those are the final answers you get for the first 4 terms. Example 4 is more stuff on factorial. And they want you to evaluate this. Well, I mean, looking ahead and looking at both of these at the same time. So look at these as like a package, a 2-example package deal. Evaluating this one is a pretty straightforward, simple task, especially if you have a calculator to help you, and especially if you know that there is a factorial, not a button probably, but a factorial function that's programmed into your calculators. So as long as you know what buttons to press to access the exclamation point on your calculator, it's probably on some menu somewhere. In class, we will point this out. It's probably some probability menu or some. Let me grab those yellow calculators quick, actually. I mean, if you're at home right now, who knows what calculator you have handy at home, but in class these days, in 2018, we have these yellow mamma jammas. So, yeah, it turns out to be this PRB button, which kind of is shorthand for probability, because factorials have a lot to do with probability, which you'll see eventually here in this unit. Not now, but later. So to figure out 10 factorial, for example, first you would hit the 10, 1, 0. Then you would go to your probability menu, go down to the exclamation point, hit enter. So now your screen says 10 factorial, 10 exclamation point. Then you would hit enter, and it's a giant number. And anyway, you can basically throw all this into your calculator at once and get a final answer. Easy peasy, nacho cheesy, windy breezy, coffee sneezy, lemon squeezy. But here, I want to show you a quick little trick here, which is not super needed here, but it's needed here. So anyway, 10 factorial, when you like expand it out, what does 10 factorial mean? Well, it means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, looking at the bottom here, 2 factorial, 8 factorial, couldn't you just think of 10 factorial as 10 times 9 times 8 factorial? Because 8 factorial would like finish that all the way down to 1, you know? So that's the little trick that I'm going to show you here. Rewrite 10 factorial as this, because it is the same as 10 factorial. And then guess what? What do you think happens? Like, why is that a nifty, useful thing to do? Because these cancel, and you're left with 90 over 2, basically, which is 45. And your calculator would tell you this as long as you plugged it in correctly. Now over here, you pretty much need to do that approach. And so look, n plus 1 factorial, when you expand it, would be like, okay, it would start with n plus 1, and then it would be multiplied by, like, what's 1 less than n plus 1? What would be the next number down? You know, well, it'd be n plus 1 times n times n minus 1 times n minus 2 times n minus 3 times n minus 4, right? But considering what's on the bottom, we would just rewrite it like this. N plus 1 times n, and then just putting the factorial on here. That would theoretically keep it going, but we stop there because this is what's going to cancel with what's on the bottom. And so the final answer here is just n plus 1. See that? Moving on. Oh, man. Moving on. Would not be surprised if that's all we were able to accomplish in a single class, right? So this 5.1 section, it might take more than one class period, just FYI if you're sitting at home. But I'm going to keep on going, and maybe you should too. I don't know. Here we go. Summation notation. Summation, which what smaller word lives in the word summation? That's right, sum, S-U-M, as in adding crap together. But here we go. A summation is when you, well, spoiler alert, I guess, add the first n terms of a sequence together. What the heck is this? Well, this, my friends, is a Greek letter known as sigma, okay? So it's just some notation that we have come to use to represent that we're summing stuff up, that we're adding a whole bunch of stuff up. So this summation, so it means like sigma, and then down here we like, okay, oh, this, oh my gosh. Man, technically, people, I think I noticed this last year as well, that I had a little goof. This should actually be a stinking N. How about that? Hope I noticed that in class again this year. But so it's like we're adding up a bunch of nth terms, and this is where we start. So n equals, looks like we're starting at with n equals 1, and then we're going all the way to whatever. So here we're just going to n. So here it'd be like we'd start at 1 in for here, and then we would like add up all the terms going from 1 and stopping when we get to this. So, you know, you stop whenever you get to whatever that is. Anyway, here's what a textbook would say about summation notation for like a sequence, which you can now start calling a series. But I'm not going to overly emphasize that, you know, that specific lingo. But so this is what a textbook might show you for like summation notation. But let's get into some examples so you really know what's going on, okay? So here we go. Here's a good example. Now we're using I, okay, because we have an I here and I here. So this is going to be like, I guess not our nth term, but our ith term. Anyway, so what this means is that we're going to be adding up a bunch of these terms, starting with the term where I equals 1, and then we're going to like get the next term will be when I equals 2, and then the next term will be when I equals 3, and then I equals 4, and then I equals 5, and then we're going to stop at the term when I equals 6, because it says that right here. So, well, this is what I just got done saying. First thing we're going to do is plug in what's down here, 1, right? So 1 squared plus 1, and then 2 squared plus 1, and then 3 squared plus 1, 4 squared plus 1, 5 squared plus 1, and we stop at when we stop. So we start when I equals 1, we stop when I equals 6. And now it's just a matter of, oh man, just crunching this out. So all this is 2, all this is 5, 10, 17, 26, 37. Add them together to get 97. This next example, again, feel free to pause if you give yourself time to write this stuff down, eh? This next example, now we're using an index of k, which is fine, whatever. Could be an n, could be an I. Just saying the most common, I don't know. I don't know if I is the most common or n. I wanted to say I. So I would say it's a tie between I and n as being the most common variables, which are kind of called indexes here. But again, I don't want to overly emphasize what the lingo is. Anyway, so it looks like here these are going to be the like nth terms, or the kth term. Right? So all the terms are going to be -2 to some power -5. We're going to start by plugging in 4 and then building each term until we get to k equals 7. Okay? So we start by plugging in 4. And again, we're adding all this stuff together. That's what this sigma notation even means. So the next term is going to be the k equals 5 term. The next term is going to be this, but the k equals 6 term. And then finally we stop at the k equals 7 term. So you just have to very carefully calculate or evaluate, number crunch, all this stuff, which I don't think I need to drag out by explaining. And just, feel free to pause the video just to make sure you understand how we're ultimately getting to be -100. Well, this looks crazy, doesn't it? So here we go. It looks like we're starting with I equals 1 and going all the way until it's I equals 5. And, oh man, where are we going to plug in the 1 and then the 2 and then the 3? What the heck is this going to be? Prank number 2 on you this time, not me. Yeah, each term is just 3. Like, that's what each term is, just adding up a bunch of 3's. But yes, we still have to go through the whole series of, like, this is where I equals 1, so of course just 3. This is where I equals 2, but it's just the same old 3. This is where you let I equal 3. This is where you let I equal 4. And yep, this is where you let I equal 5. So you still go through the whole I equals 1, 2, 3, 4, and 5. But every term is just 3, and therefore the final sum is just 15. Okay, how much longer? Oh yeah, that's why there's another 5 slides here. Okay, all right, okay. So the final example here in these notes, now it's like we're going to go backwards. So now they're giving you a summation, okay, which looks like this. And they want you to come up with the summation notation, the sigma notation. Remember, this Greek letter is known as sigma. Okay? Now, something I want to point out, especially here. 1 cubed plus 2 cubed plus 3 cubed. Why didn't they just write the summation as 1, because that's what 1 cubed is, right? 1 plus 8 plus, what is this, 27, and then whatever 7 cubed is. Is it 249? I don't know. It's 300 something, I don't even know. But why did they write it like this? And you know what? The answer is that they're actually trying to help you by not simplifying that this is just a 1, that's just an 8, that's just a 27. When they leave things unsimplified, it's actually easier to tell where each term came from. If this was written as like 1 plus 8 plus 27 plus, all right, what the heck is 7 cubed? 343. Okay, that sounds familiar. I knew it. I did say 300. Anyway, so if they were to write it as 1 plus 8 plus 27 plus 343, it might be tougher to tell like where all these terms came from, and so in order to figure out that this is just going to be something cubed, you know. So look at from term to term to term to term, you know. What's changing? Well, it looks like the base is what's changing. So it's going 1 and then 2 and then 3. So this is what's going to get the I. And we're going to start by plugging in 1. And what's the final thing we plug in for this I? 7. So this is the final answer for sigma notation from 1 to 7. And each term is I cubed. So it's like in the future, whatever is increasing by 1. So here's a good rule of thumb, okay? Just let me start that again. So here's your pretty good rule of thumb. Whatever is increasing by 1 from term to term to term to term, that's what you're going to use an I for, or an N if that's what you're going for. But that's what's going to be your I in the sigma notation, okay? So over here, 1 plus 1 over 3 plus 1 over 9 plus 1 over 27, all the way to here. Now, real quick, this one's being a little bit more mysterious, I think. Yeah. In case you didn't know what you've been listening to this whole time. So, if you are... If you're taking this class in the first semester, then we're approaching Christmas. It's December. It's early December, but whatever. Anyway, as I was saying, this one's being a little bit more mysterious with where these terms are coming from. But then it's like, trust me, with this, I know it might be confusing at first, but this is actually really trying to help you down here. So it's like, if this was being like extra, extra, extra helpful, this second term would actually be written as 1 over 3 to the what power? First power. Plus 1 over 3 to the second power. Plus 1 over 3 to the third power. And so what does it make this? 1 is 1 over 3 to the, that's right, 0 power. Okay, and then, plus, dot, 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 same thing. So check this out, people. What is increasing by 1 as we go from term to term to term to term? Well, it looks like the exponent on the 3 keeps increasing by 1. So that's what's going to get the I in this general term here in sigma notation. Okay? Ooh, man. Actually, oh, man. Well, I almost wish I would have just made this I at first. And anyway. So check this out. If our first term is supposed to be 1 over 3 to the 0, and if we're going to start with I equals 1, like it seems like that's the norm, right? We're going from 1 to something. So like, what's the last thing we're going to be plugging in for I? It looks like, weirdly enough, so we start by plugging in 1, and that way we're starting with 0. So because 1 minus 1 makes 0. But what's the last thing we're plugging in for I? Looks like it's n. And so that's it, But yeah, so if we're starting off with 1 over 3 to the 0, then we need to make this exponent I minus 1. Now, with that being said, and I know that might seem weird, but check this out. What color am I got right now here? Blue? Okay, good enough. What if I just wanted this part of it just to be like 3 to the I power? Can I still be starting off at 1? No, because the first term is supposed to be that. So if this is how I want to write my general term, guess what the first thing we're plugging in for I is? Not 1, 0. And guess what? That's totally okay. I mean, look back here where like the first thing we were plugging in was a 4. So it doesn't have to be a 1, Here it was because of how we did this thing, but if it was just 1 over 3 to the I, then guess what? We're starting by plugging in 0, and if this is what we're plugging in for I, what's the last thing we're plugging in? It'd be n minus 1. So guess what? Either one of these versions is correct. Heck, we could make a version of this where we're starting off at I equals 6. But this, I don't know which one would be more common that people would go. But these two would definitely be like the most common ways to answer this question, whether you're starting off with I equals 1, it's got to be this, and it's got to be this. But if you're starting off plugging in 0 for I, then it'd be this, and it'd be that. Bottom line. All right, now, I would definitely be shocked if we got to this the day of, okay? Like, in fact, I have a little bit of reason to actually, save this for not much later, but later, okay? But I'll just do it now because it's on the same notes packet. These are some properties of sums. So our logs had properties. So guess what? This sigma stuff, these summations, also have some basic properties, and check it out. The first property says if you're just doing the sum of a constant from 1 to whatever n, the final answer is going to just be this times n. And this is more of a formula than a property. And so this example, oh man, I got to go bold. I mean, think about it. This is why this formula makes sense, right? And it is more of a formula than a property. If you were doing like the summation of 12 from 1 to 95, wouldn't this just be 12 plus 12 plus 12 plus 12 plus 12 plus 12 plus 12? You know, you might as well just do 12 times 95. And that's what this means over here. It's like whatever this is times whatever this is. But the C has to represent just like a regular constant number. And my goodness, what the heck is 12 times 95? 12 times 95 is 1,140. So, oh yeah. So now, I guess the first real true property would be this. If you were finding the sum of something where there was like a coefficient involved with this sort of thing, you could actually just, and remember, it's a regular constant number, you could just bring it way out in front of the whole sigma expression. Case in point, if you were doing the summation of 7i squared from 1 to 40, you know, this property says that you could just bring the 7 out in front, and now it's just the sigma of I squared from 1 to 40, and then just multiply the whole thing by 7. So you can bring coefficients out in front of the sigma. That's a property. And here's the next property. And is there another? Yeah, I didn't think there was another property. So this is the last one. So here we go. If you have multiple terms over here, whether it's plus or minus, whatever, if you have multiple terms from the sigma, kind of, well, just like this one, or let's see here, where was an example? Like this kind of thing, and this, you can actually rewrite it as separate sigma expressions. You can kind of break it up. So like over here, you could actually break this up. I equals 1 to 72 of 3i plus and then the 8 separate. So 2 separate sigma expressions for these 2 separate terms. Now, I know you're probably busy writing this down, but listen. Could we actually take this further, and as far as like applying other properties and formulas? Yeah, I mean, the other property says that we could take this 3 and bring it out in front if we were so inclined. And the first property, which is more like a formula, says that, hey, we could very quickly calculate what this answer is just by doing 8 times 72. Anyway, so, wow. That was a doozy. And yeah, like, most likely not a one-day class, a one-class thing. But that is the first section of Unit 5.